This lecture will be the beginning of our study of language models, which play a crucial role both in the scientific study of human language processing and in natural language processing technology. I'll motivate it by a few examples, once again, from speech perception. In each case, just listen to what you hear, maybe note down what you think it was, and then we'll compare to some possibilities. Here's the first one. It's not easy to recognize speech. What you heard is phonetically compatible with any of the three possible sentences that I've illustrated here, but you probably heard the third of the three. This is actually a really famous example from the speech recognition literature. Let's go to the second example. I saw a van. What you heard is compatible with either of the sentences that you see here, but of course, this one is vastly more plausible as a sentence. The first one is almost ungrammatical sounding. And you probably heard the latter, not the former. Here's a third example.
The sale of a boat.
In this case, you might have heard either of the following two, or you might have been uncertain as to which one it was. Unlike in the first two cases, this is a case where either of the two would be plausible, either is reasonable, but usually people will report hearing one or the other. What I want to focus your attention on is the difference between hearing that and hearing the next example here. A boat's sail. This one, once again, you could hear either the SAIL or the SALE interpretation of the word sail, and reflect for a moment on whether one sounded more like the part of the boat sale and one sounded more like the transaction sale. And once again, people report different things, but both are possible, and you may feel that one is more plausible in one word order than in the other, and that's interesting and worth thinking about. Here's another similar type of example. A dog's tail. Once again, you might have heard either of these two, and compare it again with the tail of a dog. You might have heard either of these two. Regardless of what you heard, take a moment to reflect on the fact that either of the two interpretations of the word sail, tail, are plausible, given what you hear and given the sentence context, but you may be differently biased in each case. You may place different bets on what the speaker intended, sail or tail, SALE, SAIL, TALE, TAIL, depending on the context. Now I'm going to move over to another kind of motivating example. This is probably something that you're familiar with. This is a famous viral message. I'll read it here. Do you find this simple to read? Because of the phenomenal power of the human mind, most people do. According to research at Cambridge University, it doesn't matter what order the letters are in. The only important thing is that the first and last letter be in the right place. The rest can be a total mess and you can still read it without a problem. This is because the human mind does not read every letter by itself, but the word as a whole. Talk about cool. The study from the University of Cambridge is apocryphal. It doesn't actually exist, but it's quite likely that you encountered this at one time or another in your life. So now, note carefully what it actually says here. The claim here is that the reason that you can read words so easily like this is because the human mind does not read every letter by itself, but the word as a whole. Let's test that hypothesis out. So what I'm going to show you on the next slide is I'm going to take a different passage and I'm going to scramble it in one of two ways. And let's see how easy it is for you. Here's the first example, the first version. You can pause here, pause the video, and take as long as you want to try to figure out what this is. I really encourage you to do that. And what I think you'll find is that if you work really hard, you can work out what all the words are. So take a moment to do that if you want, because what I'm going to show you next is another version of this, where I've scrambled the words internally in exactly the same way, but done something different with the words in terms of where they are in the passage. Here we go. And what you probably experience here is that it's now extremely easy to read the text, despite the fact that every word internally is scrambled in exactly the same way as in the upper version of the text on the top half of this slide. The reason that it's so much easier is that the words in the bottom half have their order preserved, only the internal ordering of the letters is scrambled. Whereas in the upper case, in the upper half of the slide, I've not only scrambled each word internally, the letters, but I've also scrambled the words in their order in the entire passage as a whole. And what this is an illustration of is that it's not just the fact that you have to have all the little pieces internally. Having the broader outside context in which that unit, that word appears, also is important in the recognition process. And it can make all the difference between a highly effortful process of decoding in the upper half of the slide versus an almost effortless process of identifying and recognizing very quickly in the bottom half of the slide. All of these examples that I've shown you in speech perception and in reading are an illustration of the fact that context guides our expectations about what words are likely to appear where, and that process actually dramatically affects, and we could even say shapes, how language understanding unfolds. We're going to model this using the tools of probability theory. The fundamental quantity we're going to be interested in is the joint probability of a sequence of words. So let's say that it's an n-word sentence. We'll think of that as the joint probability of the words 1 through n. As a proviso, generally we also have to take into account the fact that the sentence ends, so we also want to include as the very last event that we're going to model the joint probability of, that a special event being this sentence is over. So what I want to do is now intuitively sort of get some intuitions running about like what this distribution might look like. Note that unlike previous distributions we've looked at, it has to put probabilities on variable length things. So what I'm going to have on the in the left-hand part of the center of the slide is I've just written 4 sentences, and to the right of this I'm going to show you the joint probability of each of these sentences in each of 3 language models. So a language model is going to be something that gives us as fundamental quantity the joint probability of word sequences. Now, because when you have lots, so any individual word is generally not that probable in its context. Its probability may be a few percent. It may be actually well under 1%. Once you start, and of course the joint probability is the product of the probabilities using the conditional probabilities, using conditioned on the other words that are involved. Once you start multiplying a lot of these probabilities together, the joint probability gets to be a very, very small number. So it's useful to look at this in log space. And in particular, we can look, for example, the information content or surprisal, which is once again the log of the inverse probability of the event or the sequence of events. And one nice thing about this is, once again, remember that logarithms transform products into sums, and also logarithms of small numbers are simply just not so small negative numbers. And so log probabilities are much more tractable to compare and to just even keep track of and write down in this space. So first of all, here's these 4 models, these 4 sentences. Let's look at model number 1. And the log probability, the overall surprisal or information content of each of the sentences is given in that column. And you can see, interestingly, there's a couple of things to note. That first of all, the short sentence, the first 5-word sentence, has the overall the lowest surprisal, so it's the most probable of the 4 sentences. Adding a little bit of length to this is somewhat longer sentence makes it a little longer. Notice now, interestingly, that I can take a sentence that is actually as short as the first one, but actually has much more infrequent words and a slightly weird word order, and it winds up having a much lower probability, much higher surprisal value than the first example or even the second example, which has more words. Conversely, I can create a relatively long sentence, and in this model, it's the most improbable of the 4, the highest surprisal of the 4, but it has a lot of words relative to that surprisal if you compare it to the third sentence. Here's a second model. Compared to the first, of all, you'll notice that all of the surprisals are lower, so it's putting higher probability on all these things. And second, it actually puts a lower surprisal value on this long but easy word sentence than on this shorter but infrequent word sentence. And then model 3 has largely the same behavior as model 2, but the probabilities are slightly different. So this is an example of how you might have 3 different models. They'll score different sentences in different ways, but they're all doing the same fundamental task of putting probabilities on sequences of words. And that's the fundamental operation that we're interested in here. If you're interested in trying this out yourself, just briefly, our lab has actually put together some tools that allow you to easily compare a number of different language models. You can just write sentences, feed them in to a command line interface, and get language model probabilities out. There are lots of tools for this, but this one we've tried to strip it down and make it very, very easy to deal with all of the technical aspects under the hood. It's called the Language Model Zoo, LM-Zoo. And we have a number of interesting language models that we have collected in the zoo, and we're continuing to add to them. So you can try that out. It's very easy to install and try out. Now, going back to the example of speech perception. So what role might language model probabilities have in speech perception? Well, if you think of the problem of speech perception as Bayesian inference, as we've advocated for earlier on, then it actually naturally falls out. So if you have a phonetic input, which I'll just call input here, the problem of identifying what you're hearing, the sentence that you're hearing, is a problem of putting a posterior probability on the word sequence in question, given an input. And Bayesian inference tells you that this decomposes into a quantity that is proportional to the likelihood of the input, given the word string, which is how much did what you heard actually sound like any particular possible word sequence. For example, it's not easy to recognize speech. If I say that normally, it sounds quite similar to what I would say for it's not easy to recognize speech. They both sound a lot like it's not easy to recognize speech. So that's the likelihood component. And we've talked about that earlier on in other sessions. But what we're focusing on here is that the other part of the Bayesian inference is the prior. And the prior is simply just the prior probability of the word sequence, irrespective of what the input is that you heard. And that's actually a fundamental term in the Bayesian inference in speech perception, and in reading for that matter. So I'll take those examples about tails and sails of dogs and boats, and I am feeding those sentences that include those, and in order to make them complete sentences, I'm starting them with the words that was, and then I'm just looking at once again, the joint surprisals, or the log of the inverse probabilities of each of these sentences in each of the three models. And there are some minor differences, but there are a couple of patterns that I want to point you to. So first of all, notice that there's some variability here, but if you look at a dog's tail, T-A-I-L, versus a dog's tail, T-A-L-E, all three of the models put a lower surprisal. They more strongly expect this last word here to be tail, T-A-I-L, than T-A-L-E. So this fourth row here is a greater surprisal, lower probability than the third row here. The second thing, we see something interesting with the cases of sails and boats. So the sail of a boat, that context, has S-A-L-E favored over S-A-I-L in all three models. You'll notice that this line has a lower surprisal than this line. Okay, but if I switch the word order around and I say it's a boats as the context and then have this word, you can see that the joint probabilities, the surprisals, flip around. And in this case, it is the former of the two that has a lower surprisal than the latter of the two in all three of the models. So this might loosely predict, for example, that if it's a boat's sail, that's going to be more biased to S-A-I-L than the sail of a boat, which might be a little less biased to S-A-I-L and maybe a little more biased to S-A-L-E. So that's the kind of pattern that might be predicted from the role of the language model as a prior in speech perception. So a Bayesian theory of speech perception might make that prediction. And it turns out that there's literature that shows that those kinds of predictions really do come out in a fairly fine-grained manner. They're easier to tell from those really stark examples like I saw a van. But they do actually come out in a wide variety of contexts, because speech perception ubiquitously involves phonetic ambiguity, and context is ubiquitously relevant and usable to guide inferences in the face of that kind of ambiguity. And that's what language understanding is always about, is inference under uncertainty, ambiguity. Okay, so those are language models that we have estimated by artificial models. But what about human cognitive subjective probabilities? How do we get at those? And it turns out that from the very earliest years of information theory and around the same time as the dawn of cognitive science, Claude Shannon developed a guessing game closely related to what's called the closed task of Taylor in 1953, which is widely used now, which helps us understand conditional probabilities that can be combined together to get joint probabilities. And then those are going to be estimates of, say, human probability distributions. And the guessing game goes as follows. I'm going to ask you letter by letter to guess what letter comes next. And I'd like you to play along with this. So I'm going to start off by just asking you, imagine you're at the beginning of some sentence, and guess what the next letter is. And for at least the first few examples, why don't you try doing this yourself? What do you think is the first letter? A lot of you might have guessed the letter T. Makes a lot of sense. T is the beginning word of the, and the is an extremely common way to start a sentence. In this particular case, you were wrong, so guess again. Okay, you might have guessed is another common way. It's wrong too. Here are a few more guesses that you might guess, and eventually, if you guess long enough, you'll get the right letter. It is W. So I'll put W there. Now try guessing what the next letter is after the word W starting off a sentence. So notice that the context here is not just the word W, but it's that you are at the beginning of a sentence and the first letter was W. Go ahead. You might guess H. That's a very, very common way to continue a sentence after the first letter being W, but that turns out to be wrong in this example. Guess again. At this point, you probably got it right. You probably identified that it's E. There are a few other possibilities, but it's very likely to be E. What do you think is next? R might be a possibility. T might be a possibility. Those are not right. It's actually this space in this particular sentence. I have the advantage of knowing where the sentence is. So I'll put in the space. That little character like that is a representation of space. Now you can guess what the next character is. A is the next, and now I'll just continue on, and you feel free to stop it at any point and guess as long as you want to see if you're right. Okay, that's an illustration of how this might unfold, and your guesses might not have been the same, of course, as the ones that I illustrated here, but this, I think, illustrates sort of a typical profile of how this works. So a couple things to note. First of all, not all different parts of the sentence are equally hard to predict. You'll notice, for example, that the beginnings of words generally tend to be harder to predict, and that's because words have a lot of internal coherence. There's a lot of information among adjacent characters. Furthermore, even at the beginnings of words, not all words are equally hard to predict. So, for example, this is probably a lot easier than a lot of other particular cases. This is maybe a little easier as well. And that predictability profile at the letter-by-letter level, really, especially at the beginnings of sentences, is pretty interesting, and it's not uniform. But at the word level, you can also play this game. It's a lot more frustrating because you're not guessing from 26 letters plus the space. You're guessing from a vast inventory of possible words, and so it gets a little more frustrating to play. But there's a lot of information that we can glean by getting people to do this guessing process about the kinds of expectations that they're deploying. And it turns out that empirically, and we're going to cover this later on, that those kinds of expectations actually seem to play a huge role in guiding how language processing works in the human mind, both in comprehension and in language production. Now, a plausible hypothesis, setting this in the context of human language processing, is that these kinds of expectations, these kinds of guesses and predictions about likely versus unlikely words in context and letters in context, play a role in how our language understanding systems are so incredibly robust. So to illustrate this, I'm going to play you an example that I take. This is my recording of an example from from a naturalistic corpus. This was actually conversational speech, but I don't have the recording, so I'm just going to play you my own recording of the transcript. I found out that my grandmother was one of a twin. So this is the sentence that you heard, and I want you to notice a couple of things. First of all, there was a disfluency here. So the speaker, and my capitulation as well, uttered the word and then used that and then went back to the beginning of the sentence. And before noting it on the transcript, you may have forgotten it by the time you got to hearing the end of the initial sentence. This is stuff that we mentally edit out of our own minds as we listen to people talking to us, as we listen to speech in our environment. Another thing that you may also notice, so this is sort of implicitly edited out to the word I. Another thing that you may notice is that one of a twin is sort of a weird thing to say, but you probably had no trouble understanding what the speaker meant to say. And if you wanted to say what the speaker intended to say, you could probably have some very specific guesses. You might guess that the speaker meant to say a twin, or one of a pair of twins, or one of a set of twins. Any of these things might have been what the speaker intended to say. So our robust language understanding capabilities are not just about identifying what's wrong. They're also about identifying what the speaker meant, and even farther, identifying what the speaker might have intended to say to convey what they meant. Another example of this comes from an experimental study in robust language comprehension by my colleague Ted Gibson.
The businessmen benefited the tax law significantly.
What did you hear? The literal words were, the businessmen benefited the tax law significantly. Is that what you remember? And in terms of the meaning, who benefited or what benefited from what or who? Literally speaking, the sentence says, the businessmen benefited the tax law. So it's the tax law that benefited and the businessmen benefited it. But you probably interpreted it as if the businessman is the one who's getting the benefit. That is, you're interpreting it as if the word from were here, but it's not actually here. And you might actually, if you thought about it before I gave you the example, you might actually have remembered, oh, maybe the word from was even there. That's what's called sort of sometimes a noisy channel inference effect. And that's something we'll study in greater detail going forward. But these are all examples of the role of the language model, the expectations about word sequences, playing a strong role in language understanding, both in speech perception and in meaning interpretation. From the technology point of view, language models play a role in all sorts of things, including artificial speech perception systems, error correction like this. But one other example, which actually is one of the very earliest uses of natural language processing technology, now over 50 years ago, is in the problem of speaker modeling. So very famously, you may know that the Federalist Papers, at the sort of dawn of the U.S. Revolution time, were authored, but they were authored by this pseudonym Publius, and there were actually three people who variously authored or co-authored the Federalist Papers: Alexander Hamilton, James Madison, and John Jay. And there's the question of who authored which papers is of interest in political science and history, but we don't actually have a ground truth for most of the Federalist Papers. And so there have been classic studies of trying to figure out, well, who did it? Well, there are differences in style of how these three people wrote, and you can get other texts that each of the three of them wrote and look at those differences in style. And you might learn an author-specific model, which is a language model that's now conditioned on an author's identity that predicts word sequences. So now there's a Bayesian inference, which is natural, which is if I want to figure out who wrote a text, that's a conditional distribution of author given the text. And so if I have a author-specific language model and a prior on authors, so for example, John Jay wrote fewer of the papers than Hamilton or Madison did, then I can actually perform probabilistic inference to try to guess at the authorship of texts for which I don't know the author. These methods have also been used, for example, to figure out, did Shakespeare write all of his works attributed to him, and many other problems. Okay, there are many, many different ways of building language models. None of them, in terms of current technology, are perfect. Variously, there are probabilistic grammars which use methods from linguistics to create symbolic hierarchical discrete models, and then you can put probabilities on those. There are contemporary neural network models which perform extremely well but are hard to interpret. And there are n-gram models, which are just simply breaking up a sentence into smaller contiguous word sequence chunks and thinking of those chunks as the elementary components from which a sentence is comprised. None of these are perfect. They have various disadvantages and advantages. Today we're going to focus on language models that are n-grams, partly because they're just the simplest to break into. They're conceptually useful. They also are applicable in terms of understanding some interesting things, potentially, about human language knowledge. But this is not a claim that these are satisfactory models of human linguistic ability. They're definitely not. They're also not state-of-the-art models from a technological standpoint today, but they're still of interest in terms of gaining experience and understanding and expertise and conceptual clarity in how you fit models on rich language data sets and how you might consider some of the challenges and address some of the challenges that arise.